Hello everyone and welcome to Calc Lesson number 36. Today we are still going to be analyzing and graphing functions. However, today we're going to be looking specifically at radical functions. So just like in our last lesson, we want to start by just remembering what we can get from our original function, from our first derivative, and from our second derivative. So these same three boxes are here. Our original function helps us to find our x and y intercepts and the end behavior. Our first derivative will help us to find any critical points to determine increasing and decreasing, and then relative extrema. And our second derivative, we can find our points of inflection, and then we can analyze concavity. Additionally, with radical functions, we're going to be expressing those radicals as a rational exponent, and then we want to take a quick look at the numerator of those exponents. If our numerator is odd, that tells us that we're going to have a vertical tangent. So for example, if we have x to the 1/3 power, since 1 is odd, we would have a vertical tangent, and just to note that a vertical tangent can be a point of inflection. If the numerator of our exponent is even, then we're going to have a cusp. So for example, x to the 2/3 power, since 2 is even, that will happen, or we will have a cusp, and a cusp cannot be a point of inflection. So we're going to take all of this information and apply it to a couple of examples, just like we did in yesterday's lesson. So the directions for the examples in today's lesson are the same as they were for lesson 35. For each of the following, we're going to analyze the function by filling in missing information where applicable in the table that is provided. We're going to then try to sketch our graph using what we have found. Okay, starting with number 1, here our function f of x equals x to the 2/3 power minus 1. So I'm going to start by analyzing whatever we can just from our original function f of x, starting with the domain. So because we have an x to the 2/3 power, we want to think about the graph of y equals the cubed root of x and the domain of that function. Because the domain of the cubed root is negative infinity to positive infinity, the domain of this function will also be negative infinity to positive infinity. The other piece we get from our original function are our x and y intercepts. Remember, to find our x-intercept, we set our function equal to 0, and to find our y-intercepts, we evaluate our function at 0. So let's go ahead and do both of those things, starting by setting our original function equal to 0 to find our x-intercepts. We have x to the 2/3 power minus 1 equals 0. So x to the 2/3 equals 1. To get rid of that 2/3 power, I'm going to raise it to the 3/2 on both sides. So we're left with x equals 1 to the 3/2 power, which is really the square root of 1 cubed. 1 cubed is just 1, and the square root of 1 would be plus or minus 1, so make sure you include both. So our x-intercepts happen at 1, 0, and negative 1, 0. We also want to find our y-intercept, which we can do by actually evaluating at 0, so we would get 0 to the 2/3 power minus 1 is just 0 minus 1, which is negative 1. So we get our y-intercept at the point 0, negative 1. That's everything that we can get from our original function f of x. So from here we want to go ahead and take our first derivative. So to take our derivative of the function x to the 2/3 power minus 1, we need to use our power rule. Here our power is 2/3, so we bring it down, keep our x, and then go to the 1 less power. 2/3 minus 1 is 2/3 minus 3/3, gives us negative 1/3. And then of course the derivative of negative 1 is just 0, so we don't have to write it. So we can write our derivative f prime of x as 2/3 times x to the 1/3 power. Remember, to find our critical points, we set our numerator equal to 0 and also our denominator equal to 0. The numerator has no variables, so we don't need to worry about that one. There's nothing that would make our numerator equal to 0. Our denominator, however, 3x to the 1/3 equals 0. The only way that would happen is if x equals 0. So x equals 0 makes that undefined. That would be our critical point. Because the numerator of our function was even here, we know that what that is going to be is a cusp. Remember from the first slide, if it's odd, we get a vertical tangent. If it's even, we get a cusp, and a cusp will not be a point of inflection. Okay, from here we want to set up our number line just like we would before and analyze around that critical point. So I'm going to look at -1 and 1. What I'm looking for here is increasing and decreasing, so I want to evaluate in my derivative. So f prime of -1 would be 2 over 3 times -1 to the 1/3. The third root, or the cubed root, can be negative, so the cubed root of a negative is going to be negative. So we're going to have a positive over a negative will stay negative. And then f prime of +1 would be 2 over 3 times 1 to the 1/3 will be a positive over a positive, which will stay positive. So our function is going to be decreasing from -infinity to 0, and then increasing from 0 to infinity. Notice we only have that one change, so we change from decreasing to increasing, which means what we're creating is a minimum. So we actually don't create a maximum, but we have a minimum when x equals 0. Remember, we want to write that as a point. So to find the y value, we would plug that into our original function, which we actually already did. We have the point 0, -1. Now that's everything we can do with our first derivative. So now we want to actually jump over to our second derivative, f double prime of x. And to do that, I'm going to jump back to the first derivative that we found with our negative exponent, because that's going to be a little bit easier to use our power rule for. So 2/3 is our constant multiple. I'm going to leave that in front. Then using my power rule, I bring down the -1/3 x to the 1 less power, and be careful here. -1/3 minus 1 is -1/3 minus 3/3 gives us -4/3. So we can write our second derivative, f double prime of x. In our numerator, we just have 2 times -1 gives us that -2 over. In the denominator, we have 3 times 3 is 9, and then we have x to the 4/3 power. To test for concavity, again, we want to set our numerator and our denominator equal to 0. Our numerator is just a constant. We don't have to worry. In our denominator, the only value that would make that undefined is going to be 0 once again. Again, we're going to test around, and because now we're looking at concavity, we want to test in our second derivative. So the second derivative evaluated at -1 would give us -2 over 9 times -1 to the 4/3. Now remember that 4/3 means we're taking that -1 to the 4th power. Because it's even, that's always going to be a positive value. -1 times -1 times -1 times -1 is going to become positive. So this is going to give us a negative value over a positive value will be negative. And then if we evaluate our second derivative at 1, we get -2 over 9 times 1 to the 4/3. So our numerator stays negative, and our denominator, 1 to the 4/3 times 9 is going to be positive, is again negative, which means we're actually concave down on both of those intervals. So we're concave down from -infinity to 0 and from 0 to infinity. There is no interval here where we are concave up. And then because we don't have any changes in concavity, we don't have a point of inflection. Okay, just like in lesson 35, I just transferred all of that information over to the next slide so that we can go ahead and sketch our graph together. Before we do so, I just want to highlight the fact that, remember, we determined in the beginning, because we had an even numerator, that what we would get would be a cusp and not a vertical tangent. So what happened was we did find at x equals 0, we have a cusp. It's not differentiable, so it's not a point of inflection, and there's no change in concavity. So just tying all of that together. Now we can go ahead and take the information that we found and put it on our graph. So the first thing I want to put are the intercepts, the pieces that or the points that we actually found on our original function. So we have the point 1, 0 and -1, 0. Those are our x-intercepts. And we have the point 0, -1, our y-intercept. From there, I'm going to go ahead and fill in any other points. So I have a relative minimum, which I already have graphed, and that was the only other point since there was no, since there was no maximum and no point of inflection. Those are other points I would see on my graph. So now I want to look at increasing and decreasing. I know I'm increasing between 0 and infinity, so starting when x equals 0, everything after that is going to be increasing. And then from negative infinity to 0, so everything before 0 will be decreasing. And then finally, I want to look at my concavity. Now it says I'm concave down on my whole graph from negative infinity to 0, and then again from 0 to infinity. So I need to take both of those blue lines that I drew and make them curve downward, make it so that they would be jumping water, so the tangent line is above them. So I'm going to curve them downward on the right and curve downward on the left. So my final graph that I drew has that downward curve and is decreasing and comes to that cusp, stays downward curve as it's increasing. Okay, we're going to do the same thing for our second and final example today. So here our function is f of x equals 1 minus x squared, all raised to the 1/3 power. So just like we did in the last problem, we're going to start by identifying everything we can from our original function f of x, then what we can from our first derivative f prime, then what we can from our second derivative f double prime, and then we'll go to a new slide to put it all together. So starting with our original function, because we have that 1/3 power, we want to think about y equals the third root of x to determine our domain. So we can determine this domain would be negative infinity to positive infinity. There's nothing that would be different there. The other feature we get from our original function are our intercepts. So we find our x-intercepts, remember, by setting our function equal to 0. So we can go ahead and do that. So we have 1 minus x squared to the 1/3 power equals 0. Cubing both sides, we get 1 minus x squared equals 0. So 1 equals x squared, so x equals a positive or negative 1. So we have two x-intercepts at the point negative 1, 0 and at the point 1, 0. We can also find our y-intercept by actually evaluating our function at 0. So we get f of 0 is 1 minus 0 squared to the 1/3 power, which is just 1 to the 1/3 power, which is just 1. So our y-intercept happens at the point 0, 1. That's all we can really get from our original function. So from here, we want to go ahead and take our derivative. So to find our first derivative f prime of x, hopefully you recognize our original function f of x has an inside function, 1 minus x squared, and an outside function, something to the 1/3 power, which means in order to take this derivative, we need to bring back the chain rule. So we're going to start by taking that outside function and taking the derivative. So using the power rule to bring that 1/3 to the front, leaving the inside the same, and then making the exponent 1 less. So 1/3 minus 1 is 1/3, minus 3/3 is a negative 2/3. And then don't forget to use the chain rule to multiply by the derivative of the inside. The derivative of that 1 minus x squared is just going to be negative 2x. So we can write our first derivative, f prime of x. Moving anything with a negative exponent to our denominator, we're left with negative 2x over. In our denominator, we have a 3, and then 1 minus x squared to the 2/3 power. And I'm just going to write that out here so we can all see it a little bit better. Okay, remember from here, to find our critical points, we want our numerator set equal to 0 and our denominator set equal to 0. So setting our numerator equal to 0, we get the critical point x equals 0. Setting our denominator equal to 0, 3 times 1 minus x squared to the 2/3 equals 0. We're left with 1 minus x squared to the 2/3 equals 0, and then taking the 3/2 power of both sides, we're left with 1 minus x squared equals 0. So 1 equals x squared, so we get x equals plus or minus 1. So our critical points happen at negative 1, 0, and 1. From there, remember, we want to go ahead and set up our number line. And we want to evaluate around those critical numbers. So let's look at maybe -2, -1/2, and 2. We want to talk about increasing and decreasing, which means we want to talk about, or we want to plug into our derivative. So f prime of -2. Now the good news here, remember, is what we care about is only our sign. So I'm going to go through each of these and determine whether the sign would be positive or negative for the numerator and denominator. So plugging into our derivative, -2, in our numerator we would have -2 times -2, which would give us a positive numerator. In the denominator, what I want to take note of is that whatever's happening to my x value is being squared, but then that whole quantity, 1 minus x squared, is being raised to the second power. So that whole quantity is always going to be positive since it's being squared. So this 1 minus x squared to the 2/3 power will always be positive, and 3 will always be positive, meaning my denominator will always be positive. So if I plug in a -2, I get positive over positive is positive. When I go to plug in -1/2, we already determined that that denominator is always going to be positive, so all we have to do is look at our numerator. In the numerator, we have -2 times -1/2 is a negative, and a negative gives us a positive. Let's repeat with 1/2. Again, our denominator is always going to be positive. Our numerator here would be -2 times 1/2 would be negative, which gives us a negative over a positive, which is a negative. And finally, f prime of 2, denominator is going to stay positive. Numerator would be a negative times a positive, which is a negative. So what's happening is we are increasing between -1 and infinity, and then between -infinity and -1, and then still increasing from -1 to 0. So from -infinity to -1 and -1 to 0. Then we start decreasing from 0 to 1, but we're decreasing again from 1 to infinity. To identify our relative extrema, minimums or maximums, we're looking for a change from increasing to decreasing or decreasing to increasing. At -1, there's no change, we stay increasing. At 0, we go from increasing to decreasing, which makes that a maximum. We'll fill that in a second. And then at 1, we go from decreasing to decreasing, so there's no change. So there's going to be no minimum. The maximum happens at x equals 0. Remember, we want to find the actual point on the graph. Luckily, we actually already did plug in a 0, and we get out 1. So we have a maximum at the point 0, 1. So now we've done everything we needed, or we could find from our original function f and from our first derivative f prime. So now what we want to do is go ahead and find f double prime, our second derivative. Looking at the first derivative that we have, -2x over 3 times 1 minus x squared to the 2/3 power. Hopefully you recognize that to find that derivative, you would need to use the quotient rule and also the chain rule. And while yes, that sounds like a ton of fun, for problems like these, the second derivative, if it's this complicated, will be given. So in this case, our second derivative, f double prime of x, can be simplified to, in our numerator, -2 times the quantity 3 plus x squared over, and then our denominator would be 3 times the quantity 1 minus x squared, all raised to the 5/3 power. Now, if you are interested in doing that calculation, go ahead, pause this video, or maybe later tonight you can go ahead and try it. If you want your teacher to go through it with you, I'm sure that they would be thrilled to do so. But just note, if it is this complicated and that it would need this many rules, it will be given to you. That's not always the case, but when it's this complicated, that is true. So filling into my table, my second derivative, f double prime of x. Box is a little smaller than I thought. Okay, so we were given the second derivative, but we're not quite off the hook because we still need to find the places that we need to investigate. So let's take our numerator and set our numerator equal to 0. So if we have 2 times 3 plus x squared equals 0, dividing by 2, we get 3 plus x squared equals 0. So x squared equals -3, and there are going to be no real solutions to that. There is nothing that would make that numerator equal to 0. However, we also need to investigate our denominator. It's getting a little bit messy. 3 times 1 minus x squared to the 5/3 power equal to 0. Dividing by 3, we're left with 1 minus x squared to the 5/3 equals 0. Using 3/5 as our exponent on both sides, we're left with 1 minus x squared equals 0. So 1 equals x squared, so we get x equals plus or minus 1. So we want to investigate around -1 and 1 in our second derivative. Take note, we got those 2 points from our denominator. So this is where we want to look at we'll come back. Okay, so from here, evaluating our second derivative, we want to talk about concavity between around -1 and 1. Let's do -2, 0, and 2. So when I go to plug in f double prime of -2, just like I did with my first derivative, I only really care about my signs in my numerator and in my denominator. Looking at the numerator, we have a negative value times 3 plus something squared. What I noticed is that 3 plus something will always be positive no matter what that something is, and -2 will always be negative, so the numerator of this function will always be negative, and then we can just determine the denominator. So for all of these, our numerator will be negative, and then we just have to find our denominator. Plugging a -2 in to this denominator, we would get -2 squared would be a +4. 1 minus a +4 is a negative. Raised to an odd exponent stays negative. Multiplied by a +3 stays negative. So the denominator of this function would be negative. So at -2, our second derivative is negative over negative is actually positive. Plugging in 0, f double prime of 0, numerator always negative. We don't even have to worry about that one. Plugging into that denominator, we get 0 squared. So 1 minus 0 is 1. Now we have a positive raised to the odd power stays positive. Our denominator is going to be positive, but then a negative over a positive is a negative. And finally, plugging into f double prime of 2, I'm sorry, I'm squeezing this in at the bottom here. Numerator's always negative. We don't have to worry about that. Denominator, just like with our -2, we get 1 minus 4 is a negative number, raised to an odd power is a negative, multiplied by 3 is a negative, and then a negative over a negative is a positive. So go ahead and pause this video if you need to simplify those, or if you need to look through them for another minute to make sure you agree with those signs. Once you do, hopefully you realize that that means we are concave up, and then concave down, and then concave up. So we are going to only be concave down between -1 and 1, and then we're going to be concave up from -infinity to -1, and again from 1 to infinity. Whoops, it's ugly. Now we do change concavity at -1 and 1. We go from concave down to concave up, and then concave up to concave down, and then concave down to concave up. We got those values from our denominator, so this is where we need to actually look at the value of our original exponent, and because the numerator of our exponent here was odd, that tells us that these 2 points are going to be vertical tangents, which means yes, they can be points of inflection. So we have points of inflection at -1 something and 1 something. Remember, we find those points by plugging them into our original function. Because we already know we have x-intercepts at -1, 0, and 1, 0, we know that when we plug in -1 and 1, we get out 0. So because of the odd numerator of our exponent in our original function, these are vertical tangents, and they can be points of inflection, which is different from the last problem when we had an even numerator, and that turned out to be a cusp. Okay, so now we're going to take all of that information that we just found, and we're going to sketch a graph. Before we do so, I just want to reiterate that x equals -1 and x equals 1 are vertical tangents because of the odd numerator of that exponent. And then I just have a quick picture here of a sample of what that looks like on a graph. So going ahead, we're going to start graphing with the points that we know are on our graph, meaning our x-intercepts and our y-intercepts. We have an x-intercept at -1, 0, and 1, 0, and then we have a y-intercept at 0, 1. We also want to look at any of the other points we identified. So there is a maximum at 0, 1, which we already have, and no minimum. And then our points of inflection are our intercepts, so we already have those accounted for. Now I want to jump up to increasing and decreasing. So we're increasing from -infinity to -1 and from -1 to 0. So we're increasing and increasing, and then we're decreasing and decreasing from 0 to 1 and 1 to infinity. So what we really need to look at is our concavity. So notice these points of inflections are going to be vertical tangents at -1 and 1, and they are going to change. So we're only going to be concave down between -1 and 1. So in the middle here, we want to be concave down, and then we're going to be concave up otherwise. So when we go to do that, we want to make sure that we draw these as vertical tangents. Whoops. Let me try again. And hopefully we see that what we have here is that vertical tangent. Okay, great job with these two graphs. Make sure if you had any questions or anything you were unsure of, you go back, you rewatch, or you ask your teacher. Homework 36 is a worksheet, this time for analyzing and graphing radical functions, much like these two. If you have any additional questions, please reach out to your teacher.